So in this video, I'll show you that you already know what a natural transformation is. But before we dive into that, let's be remembered why we had set up the axiom of a category and functors and natural transformation. So for categories, we wanted to be able to talk unambiguously of some arrows by listing its constituent. And the axioms were made to be sure that it was well defined unambiguously. Likewise, for functors, we wanted to talk about transported arrow by its constituent, which could be assembled in C, in D. Anyway, it was just a transported arrow. And likewise, for natural transformation, we want to be able to unambiguously assign some arrow in D going from here f of x to g of y by way of a transport of f, whether it's from whether it's f transported with the functor f or whether it's f transported by the function g. We wanted to have just one way to describe unambiguously this arrow. So let's look at a few examples to see if I can back up my claim that you already know about natural transformation. So let's start with a simple example which will highlight the fact that this added condition that we have, g of f compose alpha x equal alpha y compose f of f, is really something that belongs to D. That is, D, the category D tells us what it means to be equal. We don't know by the mere definition of natural transformation what it means to be equal. This is something which is decided by the category D. So if we start with a simple case where we have a simple category C with two objects, start and finish and a trip in between, and we'll map it to the category set, whose objects are sets and whose morphisms are functions. So here we map the object start to the object, the set of all the GPS location where the GPS location is in Paris. And likewise for St. Petersburg. And in another way, we'll map it to France, all the GPS location in France, all the GPS location in Russia. And trip will be mapped to the function that takes any GPS location in Paris to the St. Petersburg Central Station. And on the other, for the other functor from C to set, it will be mapped to the function to red square, which takes any GPS location in France and maps it to the GPS location of the red square in Moscow. So a natural family of morphisms in set that we can consider is just the injection, because Paris is part of France. So if we get a GPS location in Paris, we can see ourselves as being part of a bigger set of all the GPS location in France. Likewise for Russia and St. Petersburg. But is this family of morphisms in set indexed by the object of C a natural transformation? And that means, are the two composite morphisms from above and from below equal? Well, this notion of equality is given to us by set. And what does it mean for two morphisms of set, that is, two functions to be equal? Well, two functions are equal when they map each same input to the same output. And in that case, if we travel from below, we will go from Paris to St. Petersburg Central Station, and we'll end up in that yellow dot among all the GPS locations which are in Russia. And if we travel from above, we'll end up in that red dot, which is the GPS location of the red square in Moscow. So that certainly won't be the same as the yellow dot, and which means that as morphisms in set, those two composite errors are not the same. And so this family of morphisms in set is not a natural transformation. Another example, which is very familiar probably to programmers, is if we consider the category type, whose objects are types A and B here, and whose morphism F here are functions from element of type A to element of type B. We have a functor called a list, which maps each type to the type list of A, whose elements are lists, whose individual sequence are made of element of type A, and we can map function f to mapf. It depends how it's called in different language, but we can map this function f from A to B to a function mapf from list A to list B, and that defines a functor from type to type, from the category type to the category type. And we have another functor, a constant functor delta n, which would map any type to the integer and any morphism to the identity morphism, identity function. Now, evident family of morphism in type would be to consider the lengths at the different type index. And those are indeed different morphisms because they start from different places, so they certainly cannot be equal. Whatever the category type is about, it's if two morphisms start or end in different objects, they are certainly different. And we can ask ourselves, is this a natural transformation? That is, do we have an equality of those composites? And of course, if you take the lengths of any list, the function mapf will not change the length of the list. You just have operated on each individual element. So that means this family of morphisms in type is indeed a natural transformation. Now, let's consider some special case in abstract setting, but very simple case. If we have a C discrete, let's unpack what it is. That is, we just have objects, and we have four morphisms, the only morphisms that are required by the definition of C being a category, which are the identity morphisms. Now, if we give ourselves two functors f and g, and we map into D, the only choice we have here is where do each object land. So x has to land at some chosen f of x, and the other objects as well. But as far as the identities are concerned, they have, by the definition of being a functor, they have to land of the identity of f of x. So we have no choice there. So a functor from a discrete category to D is really like a function. And likewise for G, it's another function. And now, if we give ourselves a family of morphisms in D indexed by the object of C, alpha x, alpha y, alpha z, what are the conditions for for this family to be a natural transformation? Well, for each morphism in C, we have a square, and this square has to commute, but the only morphism we have in C are the identity, and those will be mapped to the identity of f of x and identity of g of x. So the square will have the extremities made of the identities, so of course they will commute, and we have no further condition to verify. So any family alpha C with going from fc to gc for each object C belonging to the category capital C will be a natural transformation. Now we can consider what happened when C is a general category but D is a discrete category. We have to have this square commute, but giving ourselves morphisms in D means we have no choice in that. They have to be the identities. So the simple fact that we have a family in D will imply that it's the identity, which will imply that the relevant square will commute. And that means if you have a natural transformation from the functor f to the functor g, they will actually be picking the same objects. They will map the same x to the same object in D. Now, one step up from a discrete category is D being a poset. In a discrete category, we only have identities as maps. In poset, we allow at most one map between any pair of objects. So where a general category can have any kind of maps, any numbers of maps, a poset has only one between any two objects. So if this is like a categorical version of a transitive reflexive relation, like a pre-order relation. And you can see that it's the same to say, 1 is less than 2, 2 is less than 3, therefore 1 is less than 3. And to say, well, I have an error from 1 to 2, I have an error from 2 to 3, and by virtue of being a category, I have an error from 1 to 3. So this transitivity is embedded into the definition of being a category. Now, we can, if we give ourselves a family of morphisms in D, which are like witness that f of x is less than g of x, if you want, and f of y is less than g of y. So if we give ourselves such a family, is this a natural transformation? That is, if we go from above and from below, do we have the same morphism? And by virtue of D being a poset, if we start from the same object, we end in the same object. Well, those two arrows have to be equal to the unique arrow that exists between f of x and g of y. So indeed we have a natural transformation. So here the mere existence of this family automatically implies the commutation of the relevant squares by the virtue of D being a poset. Now we can ask ourselves what happened when we mix those two ideas of discrete category and poset. And that's where I claim you kind of already know what's natural transformation in this particular case. Because that means that for any x in C, we have a witness that f of x is less than g of x. And to not talk about the individual points, but to talk about some natural transformation between f and g, it really means that you're considering the function f being less than the function g, because functors are like function if we have a domain category which is discrete. So in that way you already know what a natural transformation is, which abstracts away some structure in C, but respects it. Now, another very important special case of natural transformation is when you don't just have a natural transformation, you have what's called a natural isomorphism. That is, for each morphism in D, indexed by C of this family, each of those morphisms has an inverse. So it's you will hear or read that it's natural isomorphism between f and g. But what does it mean? It means it's really a family of isomorphisms, and they are a priori unrelated unless by the fact that that they are a natural family. And this is an important fact because you can then define G in terms of f, and vice versa. But this capacity is really linked to the fact that this is a natural family. And the simple statement that there's a natural isomorphism between f and g actually really packs a lot of definition and is built on top of a lot of structure, which is one of the strengths of category theory, because it gives you a language, a global language, or a language to talk globally about some property which also exists on a local level, but which are abstracted away in a consistent manner. But we end up with a very succinct vocabulary which packs a lot of punch, if you want. And with that, I will be able to talk about the interesting subjects for me, which are the different ways that the notion of natural transformation arise, and to get a better grasp of what it means. Until then, see you soon.